So, Leetcode 847, shortest path visiting all nodes. You have an undirected connected graph of n nodes labeled from 0 to n-1. That's important information, and that one as well. Undirected means that if there is a connection, an edge between two nodes, so in a graph we have nodes, data that we store, and then connections between them, the edges. And in undirected one, if there is a way to go from node A to B, we also have a way to go from the same way from B to A. Yeah, so that is a simplification, because, for example, in a directed one, we could go from one to another, but maybe the way back was not allowed. And connected means that there is no isolated nodes or islands of nodes. Yeah? So starting on whatever node, we theoretically can go to every other node. Yeah? There shouldn't be any disconnected nodes. That's what they mean by connected. And what else? Those integers from 0 to n-1 are standard for Leetcode problems, so they usually provide us with some input representing our graph as an array of some sort of numbers. And so in that case, it's even simpler because those are consecutive integers. So we may use it to our advantage at some point. And you are given an array graph, so that's our input data, where graph on index I is a list of all nodes connected with node I main edge. So that's what we are given, and that array, as they call it, here is an example, is like a 2D list of lists inside, and the indices of the outer list are our nodes, so 0, 1, 2, 3, so consecutive integers, and the inner lists are the edges, so to which nodes from that node I have connection. And in that case, for example, it's already visualized for us. Node 0 can go to every other node 1, 2, and 3. And they want to return the length of the shortest path that visits every node. Yeah, so starting on each node, because it's a connected graph, I can theoretically construct a path to go to every other node, but there are, of course, multiple such paths. So what we usually want is to find the most optimal one, that case the shortest, and in that case, it's not even the path itself, it's just the length. Yeah, so I don't have to remember which nodes in which order I have visited. Maybe I visited a given node multiple times. I don't have to care about that. I just care about how many edges have I crossed. Yeah, so the length is the important thing. By the end, I'm returning just a single number. You may start and stop at any node. You may revisit nodes multiple times, and you may reuse edges. Perfect. And that's what we want. Even though it's a hard problem, it has a lot of simplifications. So here is our first graph. We discussed it a little bit already. And the output for that, so this length of the shortest path is 4. And below is an explanation. So here is the path itself that theoretically we don't have to store. Yeah, so if you start at 1, you can go to 0, then you can go to 2, then you can go back to 0, and from that you can go to 3. And in that case, you have visited in total 5 nodes, with one node being repeated, 0, but you crossed 4 edges, so until one of was repeated. Yes, so 3 separate ones, but because one was repeated, that's why the output is 4. And below we have another example. So here we start at 0, and we go to 1, then 4, then 2, then 3. Yeah, so in total we crossed 4 edges, and that's our output, and that's the shortest possible way how to visit every node. But take a look into that. One edge was never visited, so we don't have to visit every edge. We just care about visiting every node, and that would be another problem if they wanted us to visit every edge. So let's try to visualize that and think about what kind of solution, what kind of algorithm can we come up with to solve that problem. So let's put our graph here and let's draw it again. So we have it in front of our eyes. Let's put 0 here and then add all the other nodes, 1, 2, and 3, and create our beautiful edges, just straight lines between those circles. And let's state the objectives. What's the objective? Find shortest, find length of the shortest path. That's our objective, and that's what we can put like here, highlighted with golden font, and let's write down our next thought. So what can we do? We have to visit every node. We have to go through each one of them and find the length of the shortest path. In the language of graph theory, we would call it traversal. So we have to traverse our graph. And there are two competing algorithms for that, BFS and DFS. And always when you solve those kinds of problems, you have to think about which one would be more suitable. So let's maybe stop here and make sure that everyone is on the same page. So generally, I don't want to go very deep into theory, but just for the sake of completeness, we are always recapping very briefly what each term means. So BFS is the breadth first search, and you start at given node, then go to each of its neighbors, and then from each one of them you go to each of their neighbors, and like this. So you go like when you have a tree, you would go horizontal with horizontal lines through that tree. And in DFS you go as deep as possible first, and then you backtrack one level above and go as deep as possible, and so on. So in case of BFS, one thing to remember is that if they are mentioning shortest path, BFS generally speaking guarantees finding of the shortest path, and DFS not. So in case of DFS, we would have to find all the paths, and then we would have to compare them, and so on. So the rule of thumb is that if they mention something about the shortest path, at least the one that I follow, is that usually BFS would be better. But also with BFS, you have to be careful that if you use a queue to mark what kind of nodes you have to visit, what kind of nodes are ahead of you, that you can take a lot of additional memory. In case of DFS, you are using recursion, and in case of BFS, you are using queue, usually. Yeah, but probably there are some other non-standard implementations. So if you want to, just for the sake of completeness, draw it quickly here, how DFS and how BFS would proceed, we would need an additional node because this graph is a bit too simple, and they would look exactly the same. So in case of, we can add another node, maybe 4 would be better, because there's no 4, and we can choose 1 as a starting point. So in that case, we would, let's put it here, we would write BFS would go like that. First you go to 1, so which we have chosen 1 as our starting point. So right now we are just discussing in general what is DFS and DFS, and then we will proceed with the next steps for our problem. And that's why I modified this graph a little bit, but we will backtrack in a second. So you go to each of your neighbors. So you go to 0 and 4, for example, in that order. It depends also how you implement it, and how you order the neighbors. That might also be a difference between different implementations. And then you go to the neighbors of each neighbor. So first 0 was there, so you go to 2 and 3, those are the neighbors of 0. And that's it. 4 doesn't have any neighbors that weren't yet visited. And DFS, on the other hand, if we start with 1, it would also go there. But if we go to 0, then we go to 2. So we continue in the depth, and then we reach the end of our graph here, and we backtrack one step, and 0 has one neighbor that we haven't yet visited. That would be 3, and then we go back to here, and finally we will visit 4. And so that would be a difference between them. So in that case, either way, just this was more reminder. We are choosing, we can already mark it like that. We are choosing BFS. Okay, good. So now we have to somehow mark visited nodes, and let's think about this. So we need to know what nodes were visited. Why? First of all, we don't want to go into infinite loops, yeah? We don't want to spend time repeating the same path that we have already taken. And we also need a way in which we can distinguish between an incomplete path and a complete path. So when should we stop? That's a question that we have to ask. So we need to have a way somehow to mark the path that we have taken. So we could, for example, we have multiple options. So for example, we could create a list, and simply as we go, we add a given node to the list. So first, for example, we start at 0, we add 0, and then each node the same way as we go through the list. So that would be one option. Maybe we can even do it like this in a list form. Another option would be set. And set would allow us to store only unique nodes. So we would take a little bit less memory. So in case we visited a given node multiple times, it would just appear once. And that's the question, if we care about the exact path, or we just care about if we visited a given node once or not. And so that's something to think about. And there is even more compact way. And bitset bitmask, which we'll describe in a second. So let's write them down. So in case of a list, we would do something like that. We would go first to 0, then to 1, then to 0, then to 2, then to 0 again, for example, if we start from here, and then to 3. Yeah? And we already can see that, let's write it like that, that in that case, in the case of this path, if we start with 0, we would have to repeat 0 3 times. So this is not optimal. And also we would need to compare if everything is here. So even to mark the stop, we would have problems with the list. In case of a set, we could solve all those issues. So we could just have a set, and if we start here, we can just go to 0, let's say, then go to 1. Let's say we have taken the same path, but in that case, we would then, if we go back to 0, we don't have to add it, because set only stores unique values, and we would have a more compact form. And we could have a condition, for example, when to stop. We need to have a way to say, okay, right now we've already visited all the nodes. How to know that we visited all the nodes? So we could check, for example, is is it equal to n? Yeah. In case it is, it means we have already visited everything. So those are very good advantages of set. So this is a length n to fat. Let me put it here. Let me move it a little bit above, so it's not too crowded. Yeah, so length of that is n. So one way we could create a condition to terminate our traversal, our PFS, would be to check that's if the length is already n, and in that case we would know that we have visited every node. But there is even a better way. So we could use a binary encoding and create a mask. And so we could have binary number first 0, and whenever we enter into each node, we would switch and a digit of that number, which corresponds to a given node, from 0 to 1. Yeah? So for example, if we start with 0, we would put here 1. Then in the next step, when we go to 1, we would cross out this thing. And that would become 1, and so on. And we would ask a question always, is that equal to the full mask, which would be 1, 1, 1 in that case. So as many binary ones as there are nodes in the graph. Yeah, so the length of that would be the same as that. Yeah, and that's more or less it. So I think that we would just choose bitmask because it's the most optimal, and it gives us everything that we need for that problem. If we would run into any other issue in the implementation, we would simply go back. So let's now start implementing. Okay, let's try to put into code what we were discussing about. So we always need our class called solution, and inside this we need shortest path length method, which accepts self, and graph. Yeah, graph was our only input that they were given, that they are giving us, or that we are given. And inside we want to do some BFS loop. Yes, and for BFS loop, we've already said that we need a queue. So we need to initialize queue, and those are two main elements. And other than that, we just need to fill those blanks, and we should come up with solution like that. Here, so for queue, what will be that queue? The queue we need to get from collections, import the queue, kind of like this. I think I'm not good at spelling, so maybe I made a mistake. So that would be the queue, and what does it do? So we could theoretically in BFS start from a single node and then go to all its neighbors and so on, but we don't know which node is the best to start. That's what we have to find out. So what we will do instead of going through single one, we will investigate all possible options simultaneously. Yes. So in the beginning, we will add all the nodes as they are, and then for each of them we go to all the neighbors, and so on, and then for each neighbor we go to all the neighbors and so on. And on each step we will be like each one of those layers we will make it as a single step. Yes, and we will have some counter to count how many steps were there, and if we reach all nodes, so if we visited all nodes, then we can return this counter. So that's more or less the whole solution, the whole idea behind it. So while queue exists, we will be doing something here. So we will be checking, did we visit all the nodes? Yes. And if so, then return steps. And what are steps? Steps are simply, this is simply an integer and how many edges have we been through, but not individual one, because in a single iteration we check all the possibilities. Yes. So first we go to each node and so on, so on. Yes. So we have to do it like that to be sure that we found the best possible option. And what else? So how do we check if we visited all the nodes? We have our mask and we compare it to the full mask. What is the full mask? Full mask is 1 shifted by n minus 1. What it is? So if n equals to 3, what is this first operation? 1 shifted by 3 to the left. It's simply 1 and 3 zeros. Simple, nothing complicated. If it was 1 shifted by 5 to the left, it would be 1 and 5 zeros, and so on. So if we subtract from that 1 in binary and in decimal, 1 is the same, what do we get? This 1 turns to 0 and all the zeros turns to 1. It's a previous number. So we have 3 ones. That's our full mask. Yes, so we have n nodes, and whenever we visit a node, we turn 0 to 1. And if all the zeros were turned to 1, we get the full mask. We can even already put it here as if mask equal to full mask. Full mask already exists, mask doesn't exist. We have to get it from the queue. So let's initialize the queue. What we have to put on the queue? All our nodes. For node in range n. And n nodes. And what are the values? The same as indices of graph. So 0, 1, 2, 3, 4, and so on. That's why we can use range. And for each one of them, we mark that it itself has been visited on its own mask. So each receives a separate mask, and each one is like a single possibility of starting point, and we have to figure out which one is the best. So we can append this to our queue. Those are all the things that we are starting with. And the same thing we can take from the queue, take down, pop left. So we pop from the left, take the first one at the front, and check for it. Have we already visited all the nodes? If answer is yes, then return how many steps did we take till now. If not, then we have to check all its neighbors. For neighbor in graph on the position node, we have to compute a new mask, which is the old one plus one more one at which position? At the position neighbor. And yes, that we actually take. Next mask. Okay, and one more thing, we need to increment our counter. But on every check, on every node, not. Why not? Because we have this layer of all possibilities, yes? So we take one we go through one edge from one node and through all others in a single layer to investigate all the possibilities. But within one possibility in a layer, we just move through one edge. And how many of those are? How many nodes are we investigating currently? Size of the queue. And that's more or less it. We could theoretically return -1 as well here, but it probably will never be reached because the graph is connected. So let's run it right now. There's one more thing left that we didn't do. So this is more or less the solution. What did we forget about? We don't mark visited combinations. Here is in. So given node and masks, so visited nodes so far before we reach that node, can what can it do? It can occur multiple times. Yeah. So let's try to submit it. So we can run into some infinite loops. So what we should do? Yeah, memory limit limit. That's what I thought. We need to have a way to mark if we visited given node and mask together. Yes. So how many options for masks are there? There are full mask plus 1 options. Yeah. So 2 to the power of n. And how many options are there for a node? N option. Yeah. So we can have n nodes and 2 to the power of n masks. Okay. And here visited node and mask, we can already mark true at this place. And we can also mark it as true at this place. Just that here node is called neighbor. Node's called neighbor, and we only want to add given combination if it's not already there. So if not, and mask is called next mask. Yeah. Let's not mix up, because then you will run into errors. But at this point, we should be very close to the solution. So right now we beat 98%. You may get a better or worse result depending on some random things. So sometimes I submitted exactly the same solution and got different results here. But either way, I think it's quite good. So we beat 98% by our runtime and almost 95% by our memory. So we were quite good with managing memory, and I usually have problems with that. Okay, so I guess that's it, and see you in the next video.